so hi everyone, welcome for this new seminar. So today we have the pleasure to welcome Haroldo Lima from University of Maranhão. And Haroldo will present some work about interference, coherence, and interferometry, the physics of black hole imaging. So as usual, feel free to ask questions during the talk, and there will be also time at the end. And please, Haroldo, you have the floor. Thanks a lot for giving this seminar.
Thank you, Ivan. Good morning, everyone. Let me start by saying that it's a pleasure to be here again at Haroldo, and I would like to thank Carlos for this opportunity to be here and to present these some notes that I have been preparing in Brazil. And I would also like to thank Jordan for the support with this presentation. To start, I must say that this presentation is not going to be focused on black holes. It's going to be more about optics. But in the end, there is an important application to the black hole imaging, which is the theory that bases the Event Horizon Telescope. So I will talk about some concepts of optics like interference, coherence, and the technique of interferometry. So to begin, what is this presentation about? What do we want to do? We want to see distant objects in the sky. And since they are very far away, they look very small in our local sky. So the angular size of these objects is very small. How can we see something like that? Well, one can say that we can build like very nice and technically built interferometers or telescopes, sorry. And we can point the telescopes to these small sources in the sky. And we have, for instance, optical telescopes and also radio telescopes. But it happens that even if we manage to build a perfect telescope with perfect mirrors, and we can perfect focus match the focus point, these telescopes is going to be limited by nature through a phenomena which is called diffraction. So light has this property that it can counter some aperture, and this phenomenon gives rise to something which is called the Rayleigh criterion, which limits the angular resolution of a even perfect theoretical telescope. And the angular limit, so the minimal angle that we can see in the sky, is proportional to the wavelength of the object that we are seeing, the length of the wave that this object emits, divided by d, which is essentially the diameter of the aperture of the telescope. So even a perfect telescope would have its limitations. When we buy a telescope on the internet, usually there is this information, the resolving power of the telescope. So here you have the size of the aperture of the telescope, and here you have the minimum angular resolution that this telescope can reach. So this sign here means arcs of seconds. So you have this table here. So this resolving power of telescope is essentially given by the Rayleigh criterion for an optical telescope where lambda is the wavelength of visible light. So what happens here is that if we have a point source in the sky, this point source is going to appear not as a point, but due to diffraction, it's going to appear as a disk, which is called the Airy's disk. And if the diffraction is very important on the telescope, you cannot differ if this is a single point source in the sky, a single star very far away in the sky, or if it's actually a double star, but the Airy disk of each star now is superposed and it seems like a single star. So we say that in this case here, we cannot resolve the star in the sky. We cannot say if this is a single star or if it's a double star. So this is the simulation of a telescope with a smaller diameter. This is the simulation of a telescope with a larger diameter where we can actually resolve and say that this is not a single point source, but it's actually a double, there are 2 point sources there. From this relation, the Rayleigh criterion, you can say, okay, so in order to have a better resolution of our telescopes, we can build telescopes with larger and larger apertures, or radio telescopes with larger and larger dishes. But I mean, from the technical point of view, there is a limit, of course. And if we want to image a black hole, the size of this dish would be the diameter of the Earth, which is impossible for obvious reasons. So we cannot image a black hole using a single telescope due to the Rayleigh criterion. So what can we do? The theory of coherence tells us that 2 telescopes which are far apart of a distance b have an angular resolution which is proportional to the lambda over b. So if you compare the Rayleigh criterion with this condition here that we are going to discuss, we are going to find this condition here, you can see that 2 telescopes far apart by a distance b, they have an angular resolution which is comparable to a single telescope with an aperture size of d. But in order to get this result, I mean, this is a little bit, this is tricky. This is not so straight to see, because, I mean, imagine that I have like a point source here, very small in the local sky. And I take a telescope and I point to this source, I will have a blurry image like this one. I take a second telescope and I point to the source, well, I'm going to have another blurry image. How can we resolve something with 2 blurry images? So how can 2 telescopes can work as a single telescope with a resolution given by this expression? So the idea of this presentation is to go through the theory of coherence and to understand this precisely this property here. And I mentioned the HT, the Event Horizon Telescope, but Event Horizon Telescope is not the only collaboration that uses several telescopes spread along the Earth to simulate this angular resolution. There are other collaborations. For instance, this is a net on Netherlands, which is called a collaboration called LOFAR, which is low frequency array of telescopes. They also use these type of techniques, but to resolve all the sources in the sky which are not black holes. Okay, so to start to understand the theory behind this property, like 2 telescopes working as a single telescope with that angular resolution, I will start discussing or reviewing the Young's experiment. And we are going to see that in order to understand this property is to understand the Young's experiment in a more abstract level of details. So, I mean, standard Young experiment. It was very crucial to prove the wave nature of light. So the idea of Young was to take a point source which is very far away from this setup here. And for the moment, I will assume that the source emits monochromatic waves. And here we have 2 double slits. So there are 2 small apertures here. They are very small compared to the other length of our system. And here below we have a plane of observation where we are going to see the result of the superposition of light that goes through the double slits. And in order to explain this phenomenon, we can use the so-called Orion-Fresnel principle, which says that each point in this wavefront here acts as a source for secondary waves, And so the secondary waves, they can interfere. And for instance, if we have here a plane wave very close to the double slits, so this point here in the wave front is going to act as a source of secondary waves. And so we are going to have spherical waves arising from this first slit, and also spherical waves arising from the second one. And these spherical waves, they are going to interfere. And what we see here on this observational plane is essentially a fringe pattern, which arises from the interference of these spherical waves. From the Young's experiment, we can define here B, which is the distance between the double slits. And we can define this angle here, which is essentially a polar angle measured with respect to this axis. And we can locate a given point here by saying that, by defining phi. So from the Young's experiment, if the difference in the path of this first wave here and the second wave is an integer number of the wavelength, then we are going to have constructed interference. Then we are going to have a bright spot on that observational plane. If this difference is, an integer plus half of the wavelength, then we are going to have destructive interference. And that's why we have like that fringe pattern. We can also do like very simple trigonometry here in this image and compute that the distance between two maxima. So I have a bright point here, a dark point, and following another bright point. So the difference in the angle phi between two maxima is lambda over b. This is, we can infer this from this figure. And this result I'm going to use after. Okay, so this is very qualitative. We can do a more quantitative development of this experiment, because we know that waves, light is electromagnetic waves, so they are mathematical solutions for Maxwell's equation. And so this set of equations admits plane wave solutions and also spherical solutions. So we can compute we can define the wave that passes through slit 1. It's essentially a spherical wave arising from the slit 1. And we can also define the wave that passes through the slit 2. So we have two waves, like two spherical waves. And just for the records, in the remainder of this presentation, I'm not going to take the polarization into account. So I'm going to work with a scalar electrodynamics, where I'm only worried about the modulus of the electric field. So light is essentially this perturbation, these solutions, where which are oscillations of the electric and magnetic field, and I'm going to not going to be worried about the polarization of light, although the results can be after generalized to include polarization. Okay, so what is the intensity that we see on the plane of observation? Why we see some points which are bright and other ones which are dark? Well, what we call by intensity, for instance, the intensity of this light is the square modulus of the resulting electromagnetic field at a certain point. And well, the solution here, it depends on time, it varies on time, and it oscillates very fast on time. So we do not see instantaneous intensity. What we see is an average of these square modulus of the electric field. So intensity for us here, it's defined as the time average. So this is time average of the square modulus of the resulting electric field at a certain point. And so we can take these spherical wave solutions, sum with this second spherical solution, and we can compute the modulus of them. Usually this is a complex quantity. We compute the modulus, and then we take the time average.
Why the square? Why not just modulus?
Why not just the modulus? These definitions comes from if you define the Poynting vector. So you can define the Poynting vector, which is essentially tells you how energy is carried by some wave, and intensity is essentially the energy per unit of area per unit of time. And you can show that this quantity, the energy per unit of area per unit of time, is the square modulus of the electric field. That's why. And so if we take these two solutions here, we end up with something which is given by this. And here, so the intensity is going to be dependent on this omega tau plus phi, where omega tau is essentially the time difference where the two waves takes to reach the point P. So we will have some certain points where this argument of cosine is 0 to pi, 4 pi. So this is going to be 1 plus 1, the bright points that we see on the fringe. And we also have some points where this is going to be pi, 3 pi over 2, etc. And these are the dark points on the plane of observation. So electromagnetic waves can Maxwell's equation can explain very well Young's experiment. This is what we see usually in textbooks, but unfortunately, purely monochromatic waves, they do not exist in nature. This is an ideal wave. The better that we can do is to build a quasi-monochromatic beam, which is essentially a beam which has a central frequency, and then you have a bandwidth. And this bandwidth goes from, so the frequency goes to omega, which is the central frequency, plus delta omega, and omega minus delta omega. So this is called quasi-monochromatic waves. This is the best that you can do in a real experiment. So a beam of quasi-monochromatic waves is described by this is essentially the sum of several monochromatic waves, but with different frequencies. And one can ask, well, what happens with the Young's experiment when we, instead of a perfect monochromatic wave, we had a quasi-monochromatic waves? Would we expect interference fringes or no? Well, just for completeness, we can multiply this expression here of the electric field of a quasi-monochromatic beam by some exponential of a kx minus omega tau, so a given frequency. And we can rewrite this as something that reminds a monochromatic wave, but with an amplitude that varies on time. And this is a phenomenon that we call as beating. So when we have two waves which oscillates in very near frequencies, this creates a beating which is essentially reminds a single monochromatic wave whose amplitude varies on time. And well, our goal now is to clarify if in the Young experiment with the quasi-monochromatic waves, we would have also interference fringes. So we can do again that same calculations that we did in the last slide. We know that intensity is the square modulus of the resulting electric field at a point P, and take the time average of it. And if we perform the Young experiment with a source which is quasi-monochromatic, what we have is something like this. So here we have which is essentially the intensity of slit 1. Here we have something which is the intensity of the slit 2. And this term here is, it refers to the interference. So in the case of perfect monochromatic waves, this phase difference here was a constant. It was not a function of time. And so we had well-defined fringes. But now for quasi-monochromatic waves, this phase here, it oscillates in time. And for quasi-monochromatic waves, we can have a property which is called coherence, which is the ability that the beam of quasi-monochromatic wave has or has not to maintain this phase difference is stable or constant as the beam propagates. So if as the beam propagates, if this phase difference remains constant, we are going to have interference here. So the phase they are coherent, and so we expect to have interference. But if we have a beam of quasi-monochromatic waves where the phases they fluctuate randomly, then this time average here is going to be 0. So we do not expect to have some interference, even if you have a perfect Young experiment setup. So we expect no interference at all if these phases they fluctuate randomly. And this is a property of light which is called coherence. So there are beams that are coherent, and that are beams of quasi-monochromatic waves that are not coherent. So we can quantify this property of a beam by defining the so-called complex degree of coherence. So this complex degree of coherence measures exactly that. So the ability that a beam, the property that a beam of wave has to maintain its phase coherent. And to define the complex degree of coherence, well, we compute the resulting field here, assuming quasi-monochromatic waves at a certain point P. We compute the intensity, which is essentially the square modulus of this resulting electric field. So dagger here is the complex conjugate. And we have something like this. We have this expression here. I can multiply and divide by the square root of this factor here. So it's the time average of E1 squared plus the time average of E2 squared. And I can notice that this quantity here, if I block one of the slits and let's just one or the other slit open, the time average of E1 squared is essentially the intensity of one slit. And the time average of the electric field E2 squared is the intensity of the second slit. If I block the other and keep the two open. And I can rewrite this result as follows. So it's the resulting intensity of the fringes is the intensity of slit 1 plus slit 2 plus something here, which depends on this this variable gamma that I introduced now, which is the so-called complex degree of coherence. So this quantity here measures exactly that. So the ability that a certain beam has to maintain its coherence as the wave propagates or as time passes. So if we have coherent waves, the modulus of the complex degree of coherence is going to be 1. So that's what we had in the textbook Young's experiment. If the beams are incoherent, so the modulus is going to be 0. So the resulting intensity is going to be simply the intensity of slit 1 plus intensity of slit 2. There's not going to be interference if they are incoherent. And if the complex degree of coherence is somehow between 0 and 1, we say that we have partially coherent waves. For instance, if we perform a Young experiment with sunlight, well, sunlight is non-monochromatic and incoherent. And then we are not going to produce any interference fringes. If we put just a double slit on sunlight. For instance, if you perform a Young experiment with a LED, the light emitted by a LED, LED is quasi-monochromatic, but it's not coherent. So there's not going to be interference also, interference fringes. And if you perform the Young experiment with the laser, well, laser is a special type of beam which can maintain its coherence for long distance. So it's almost perfect coherent beam. Then you expect to produce some interference fringes if you put a double slit in front of a beam of laser. So the light's not characterized only by its frequency, but it also characterized by its degree of coherence.
There's a square root missing, right, on your equations. Plus 2 square root I1 plus times I2.
Yes, it's 2 square root. Yes, exactly. I just missed it from copying from here to here. Yes, yes.
Remind us what is tau?
Okay, tau. So tau is essentially the time difference that the beam of the arrival time. Yes, essentially that. Which, if you multiply by c, is the difference between the path.
So it's the difference in the optical distance.
Yes, exactly.
Okay.
The optical distance. Exactly.
The question is more historical. So Young didn't have lasers, right? So how did he?
Yes, perfect. That's a great. So instead of taking a point source, before positioning the double slit, he put a single slit on the top. So he could manage to take a non-coherent light to produce a almost coherent light with this single slit on the top of the double slit. That's
So it's a 3 slit.
It's a 3 slit. Essentially, in practice, it's a 3 slit experiment.
I think the answer is he was very smart.
Yeah.
And that was actually to produce the coherence necessary to observe the interference fringes. Because sunlight naturally is not coherent.
Because I guess most of us at school we do it with the lasers, right?
Yes, yes. So we do that experiment with a laser. But he did like this. He put a single slit on the top of a double slit. Okay, but I mean, why I'm talking about coherence and this kind of stuff? Because this has astrophysical implications. Let's now increase or abstraction on the Young's experiment again. Now let's take 2 point sources emitting quasi-monochromatic rays. What we do expect from this experiment? Well, the light coming from the source 1 is incoherent with respect to the light coming from source 2. They do not produce interference. They do not interfere. So if there was only this point source here, we would have the interference fringes that we expect from the simple Young experiment. And since this source 2 is incoherent with respect to source 1, what we expect here is to produce another interference pattern. But this interference pattern is a little bit shifted to the left if the source is shifted to the right. And well, since this pattern here is incoherent with respect to this one, the resulting intensity on the plane of observation is going to be essentially the sum of the intensity of this first fringe with the intensity of the second fringe. Since they are incoherent, the degree of coherence of this fringe is 0 with respect to this one. Now, suppose that these 2 sources, they are very close with respect to the size of this. So we are going to have something like this. Here is the double slit, and here is the observational plane. Well, the fringe pattern from source 1 is something like this. If the second source is very close to the first one, well, the second one here, the maximum of the second one is going to be very close to the maximum of the first, and then we are going to have fringes, right? We are going to have just fringes, but the intensity is double, almost double, of what we would expect of a single one. But let's suppose that this distance between these two sources is such that the interference pattern of the second one, the maximum, coincides with the minimum of the first. So we are going to have something like this. So the maximum of the second coincides with the minimum of the first. So the maximum of the first here, maximum, minimum, maximum, minimum. What's the result? What do you expect to be the resulting intensity on the pin?
Still emitting the same wavelength.
Almost the same wavelength, exactly. So if the maximum of the first coincides with the minimum of the second, then this is going to be I, let's say. And here it's going to be I. So what we're going to have is an intensity which is almost constant. So if the separation is such that the maximum of the first fringe interference coincides with the minimum of the second, then the fringes, they are going to disappear. That's the argument here. So suppose that the angular separation θ0 between these two sources is approximately delta phi, which is the difference between two maxima divided by 2. So the maximum of the first coincides with the minimum of the second. Then the fringes, they are going to disappear. And we can define some property which is called visibility amplitude, which is essentially the visibility of the fringes. So when you see fringes, this visibility amplitude is equals to 1. And when the fringes, they completely disappear, which is essentially this case here, the visibility of the fringes is 0. So this is a quantity that we can measure, the visibility of the fringes, how much we can see the fringes there. And well, let's take this quantity here. Okay, so this approximation here. So θ0 is approximately the difference between this angular separation between two maximum, which is essentially, as we computed from the Young experiment, lambda over b. So if the separation of 2 point sources in the sky is approximately lambda over 2b, the distance between the double slits, the fringes, they will completely disappear. And this property, well, you can see here this is a very nice result. It's essentially the theoretical part plus the experimental setup by Thompson and Wolf, the author of the Wolf optic book. And this is fringe visibility 1, so you can see very well the fringes here. So the 2 point sources, they are very close, such that this didn't happen yet. But as they get far apart, the fringes, they disappear. You only see a constant intensity here. So the visibility, the fringe visibility here is equal to 0. And this was noticed in the 19th century and gave birth to what's called optical interferometry. It's essentially given by this condition here. So in 1873, Fizeau and Stefan, they were trying to resolve small stars in the sky, but the telescopes are limited by diffraction. They didn't have angular resolution to do that. So what they did, they took this condition here, and they added a double slit on the top of these Marcel 8 centimeter telescopes. So instead of trying to observe the intensity of the source, they were looking at the visibility of the fringe produced by this experiment here. And they were trying to look for what's the separation of the double slits that would make the fringes disappear. Because if the fringes disappear, they were resolving the star. Because if the fringes disappear, they obey this condition, They know what's the lambda, they know what's the separation between the double slits. It was around 60 centimeters. And they could infer the angular size of the star in the sky. Unfortunately, the experiment did not work. The visibility did not disappear. So they didn't manage to make the fringes disappear. But they could put a constraint on the size of faraway stars. Because if the fringes disappear, that's because this quantity here is still too large. So if you compute lambda over 2b, this is around 0.16 arcs of second. So the size of faraway stars were much smaller than 0.16 seconds of arc. Following the same idea, Michelson from the Michelson-Morley experiment, the famous special relativity experiment, improved the technique. So they took this is a Mount-Wilson, this is called Mount-Wilson telescope. So they took this telescope, which is larger, and they added a double slit where the separation between the two slits was around 2.5 meters. So they increased this B here. By increasing B, they decreased the theta zero. And doing that in 1920, they managed to estimate the diameter of Betelgeuse alpha Orioles, which was around 0.047 arcs of second in the sun. And they improved the technique, allowing a resolution of 0.001 arcs of second, resolving even binary systems in the sky. So what's the idea here is not to look into the source directly, not to look into the intensity of the source, but to put like this double slit on top of the telescope and to see whether these fringes, they disappear. What's the size, what's the distance between the double slits that makes this fringe visibility disappear?
So for this, you need two sources, right, to see these fringes. So, but you are looking at only one star. So, how do I interpret the two sources with the one star?
I will generalize the result, but you can think as like the left, the extreme left and the extreme right of the star, or the extreme bottom and the extreme upper part of the star. You can consider these as point sources.
What matters, I guess, is the angular size of the star. So it's when you have these 2 point-wise sources of light, they have some distance apart, so some angular size. And so essentially, that's what you
are measuring.
Focus on each point. But you need to be the telescope needs to be focused on each of these points, right? Or no?
Well, since the source is very far away, I think that variable is not very important here. But if you had a close source, this would be important, because you would have to point the telescope either to one or to the other. But since they are very far away, you can just point to have distance between the two.
My question is of the same kind actually, just to understand better how it works. So at first, say you're resolving 2 points that are too close, like two sources that are too close together, and you will see the interference, and then you enlarge the slit, which is like looking at sources further away.
No, the sources, they are fixed. Imagine that theta zero is fixed. And what you can control is the distance between the double slits. So if this distance is very, very small, so suppose that B is small, then this factor here is much greater than theta zero. So this condition is not satisfied.
Yeah.
So you increase the distance between the double slits until this factor here is on the same order of magnitude of the angular size of the double star in the sky. That's the tree.
So maybe that's what you explained, but I'm still not getting my mind around.
It's better to see from the visibility. Okay. It's better to try to picture this. If the distance between the double slits are small, you are going to see this. You are going to see fringes, which means that you did not resolve the star. But if you increase the distance between the double slits, at some point the fringes they are going to disappear, and that's what you are trying to find. If you increase the distance between the double slits and the fringes here below, that you can look on the you can put the eye on the telescope, the fringes disappear. Then you resolve the.
This part I understand. I'm just trying to make the connection then with the star. So your star has a certain radius, and we want to look at, like, say, the two extremal points. But all the other points will also emit light, and you can take any two points. And
you are right. You are right. The result is not exactly the same. I'm going to.
So my question is kind of like, is it like once the fringes disappear, are you sure that these are like the two extreme points of the star? And what happens if you continue increasing B?
What you and John are essentially asking, what's the fringe visibility of not of 2-point sources, but of let's say a disk?
Yeah.
The sun. And that's what I'm going to comment on the next slide.
Okay, then maybe I will ask again if I still don't get it.
Which is the von Zernick theorem. It's the generalization of what you expect for the fringe visibility, but not for 2-point sources, but for a random distribution on the sky. For instance, a disk, which what you see, like the disk that you see as the star in the sky, or a bar, I don't know, a disk or a thin ring. It's the so-called von Zernick theorem. The relation between the spatial distribution of the source and the fringe visibility. I don't know if I have time, so I have this animation here to explain that coherence, although 2-point sources, they can be incoherent, as the waves they propagate, they can acquire some degree of coherence. And that's exactly what the von Zernick theorem measures. So I'm going to jump this part. If you want to see the waves on the lake, I can show you after. But okay, consider again Young's experiment, but now quasi-monochromatic waves and an extended source in the sky, which is not exactly 2-point sources, but for the moment I'm going just to assume that it's a one-dimensional distribution in the sky, like a line. After I'm going to generalize to a spatially distributed source. So this theorem, which is the von Zernick theorem, answers your question. It was very important. It was a very important theorem in the field of optics, proven in the 30s and the 40s. And it gives you what's the complex degree of coherence, that property of a being to produce or not interference fringes, as a function of the intensity of this source in the sky. So suppose that we have here an extended source, which is spatially incoherent, emitting quasi-monochromatic waves, is a stationary in the sense that the intensity does not fluctuate very fast in time, is far away from the double slit, and I'm assuming here scalar waves, no polarization. The von Zernick theorem states that the complex degree of coherence, that variable that we defined in the previous slide, is related to the intensity of the source in the sky through this equation here. It's the integral of the intensity, the complex degree of coherence, the integral of the intensity. There is here a minus 2 pi u. U is essentially B over lambda. Okay? And alpha here is the angular position of this distribution. So we integrate over all the possible angular positions of the source. If this is a 2-point source, then this is going to be a direct delta. at alpha equals to 0, for instance, and the second source is going to be at a direct delta at alpha minus theta 0. So this extends the complex degree of coherence for an extended source. And if you notice, this is essentially a Fourier transform. So that mathematical quantity that we defined to quantify the coherence of a beam, it's essentially the Fourier transform of the intensity of the source in the sky. Since this is a Fourier transform, this function, this u variable here, it's a frequency, it's a spatial frequency. It's like when you do the Fourier transform of a function of time, you end up with a function of a frequency. And in this case, we are performing the Fourier transform of a function of an angle, and we end up in a space where the variable is this u variable, which is called the spatial frequency. It's an analog to a frequency. And this is called the baseline. So the baseline scales with the distance between the double slits. Well, for a spatially distributed source in the sky, now it can be two-dimensional. You look at some source, and you have some intensity in the local sky. So the complex degree of coherence is the two-dimensional Fourier transform of this intensity. And we can use this result to answer your question. Now we have a disk on the sky, which we can think as a uniform disk. So intensity is uniform, but is the form of a disk. What's the complex degree of coherence of that source? It's the Fourier transform of the intensity. And well, here in the two-dimensional case, we have like two spatial frequencies, which is the projection along the horizontal and the vertical axis into the direction of the source. Okay, so it's a little bit complicated to imagine this, but we have now, it's like the projection of the distance of the double slits into the direction of the source. Okay, so you are going to have like a horizontal projection of the separation of the double slits, and also a vertical projection. Okay, and but remember that what we really measure is the visibility amplitude, is the amplitude, the visibility of the fringes. And what's the relation between the complex degree of coherence and the visibility amplitude? Well, by that definition, we can see that the visibility amplitude is the norm of the complex degree of coherence. So we have like these two concepts, the complex degree of coherence that quantifies the coherence of a beam, but at the end, the norm of this quantity, this complex quantity, is equal to the visibility amplitude. And this is a very powerful technique because we can use that, we can measure the visibility amplitude of a given source in the sky, and we can reconstruct the image, the intensity distribution of that source, just looking at the visibility of the fringes. Okay, so just very fast, that was I was mentioned to you. So 2-point sources. Okay, the visibility amplitude is given by this, by the von Zednick theory. So the visibility goes down for this value here. If you have 2-point sources, it's the values for which this cosine is -1. So if we have 2-point sources, then the visibility goes down for, well, P over lambda is equals to U, the baseline, what the variable that we call baseline, and this goes to 0 for when this is the condition is satisfied. If we have not 2-point sources but a uniform disk, which was your question, then we can now use the von Zednick theory. It's essentially to perform a Fourier transform of this intensity here, and well, we find that the visibility amplitude is a Bessel function. And the visibility amplitude goes to 0 at the zeros of the Bessel function, which are not exactly the same as the 2-point sources, but they are the scale is the same. So, well, your question it makes sense because by the end the distance for 2-point sources is different for the distance of a circular shape on the sky.
Okay, but I guess my question was more when you extend it more. So in the case of 2-point sources, it will make interference again. And in the case of a uniform disk, it stays kind of down. So this is how you could also differentiate between 1 star and 2 stars.
Yes, you can differentiate by that. Because in this case here, well, it repeats in time. So if you increase, you are going to have like this oscillation in the visibility of the fringes. And in the case of a single star, this decreases as you increase the size of the double slit. Okay. So this theorem, the Bus-Zariski theorem, was a very important theorem in this part of interferometry. So because it allows us to do the trick that event horizon telescope does, actually, which is called aperture size. So the Bus-Zariski theorem allows us to reconstruct the image source, so the source with the data of the visibility amplitude. So it's basically to perform an inverse Fourier transform. So by the theorem, we have this result. Here we have the complex degree of coherence. But I mean, the norm of this complex degree of coherence is nothing but the visibility amplitude. So we can do the following. We can put like double slits separated into the direction of the source. We have like u equals to 3 and v equals to 6 in some units. And we can measure the visibility amplitude. I don't know, 0.5, let's say. The amplitude, they are not so apparent, they are not so visible, but they still there. And well, the visibility amplitude is equal to the complex degree of coherence. And then you can change the distance between the double slits and also its orientation with respect to the source. And so you are going to scan for points in the visibility plane. So we are going to have many points here of gamma, and then you can apply the inverse Fourier transform and infer what's the intensity of the source. That's what event horizon telescope does. They do not directly image the source. What they do is to measure the fringe visibilities, and then they use the inverse Fourier transform to reconstruct the image of the source. So that's the price that you pay for not building a telescope of the size of the Earth. You have to do this additional work. And well, recall this condition here. So I can put this lambda below and write the angular size of a given structure in my image as the inverse of the baseline, the inverse of the distance between the double slits. So if the baseline is small, I can only image large features in my image. If the baseline is small, I can only see like large features on the sky. If the baseline increases, I can see smaller things in the sky. That comes from this estimation here. And that's why EHT does very long baseline interferometry. Because this distance between the telescopes, they are very large. They are actually on the scale of the diameter of the Earth. And that's why very large baseline interferometry. Okay, so just to...
May I ask you a question? So, hearing in the past already about these interferometry techniques, I think one of the very hard points is to synchronize between the different telescopes. Where does it enter here? Is it because
I'm oversimplify it. I just say that this technique is an optical telescope with a double slit on the top, but it's not actually that simple. I'm going to mention what they actually do. It's like you have two radio telescopes, and then you send the signal of the electric field to some correlator, and then this correlator processes the data. So this part, to send it to the correlator, is somehow tricky and technical, and I don't know exactly how this is done.
But is it because like what you present is like at one given time, and in a way your system is small enough that everything is happening at the same time, and then if you have actual telescopes, you need to take care of more effects,
yes,
or like atmospheric.
Yes, you have like these technical difficulties, like the oscillation of the atmosphere and the distance between the telescope, how to synchronize them to produce the interference fringes. And these are technical difficulties, but from this point of view, I don't know.
Yeah, okay, it's not from like the principal point of view.
Yes, it's just like the principal point of view. Yes, not the practical one. If you ask me to build an interferometer, I will not know how to do it. But the theory behind it. So I have an image here, which I will not show you the image first. I will show you the complex degree of coherence, the visibility amplitude, actually, the modulus of the complex degree of coherence, which is this. And I will ask you to try to guess what is this image. But I will not show you the Fourier transform of this whole data here. I will show you the Fourier transform of only a part of it, the part which is restricted to small baselines. So this here is U, the baseline along the horizontal direction, and this is V, the baseline along the vertical direction, the separation projected along the vertical direction. And we have here some points close to the origin, so small baselines. Doing the Fourier transform of this data here, not the full data, we have this. So,
sorry, can you repeat what you just said?
This is I have some picture here.
No. Yeah, I was trying to imagine what the original picture was. I missed what did you do?
I did what is called a high pass filter.
Okay.
I filtered long baselines.
Okay.
I took the picture, did the Fourier transform.
Okay, you obtained it.
I filtered large baselines, and we have this. So you can see here like large structures and thick objects. And it's also blurry because you do not have a resolution to image that perfectly. So this is for small baselines. We can only see like thick structures on the image. Now I'm going to take this, but I will filter small baselines and allow just large baselines. Then we are going to have this image here, the Fourier transform of this image. So for large baselines, we can only see like a sharp feature 0. It's not very, we cannot really see very well here, but here we have some line, here we have some edges, and that's the type of thing that is sensible to large features on the image. And well, if I increase the number of points in the UV plane and do the Fourier transform, you can see what this image is. So it's the picture of the group picture of São Pedro do Sul in 2020. Yes. Okay, so this is the Fourier transform of this data here, this visibility data here. The Fourier transform of the full data is the full image. But this is only theoretical. In general, you do not have the data of the whole UV plane. Okay? But the message here is that small baselines can only see thick features on the image. Large baselines, they are sensible to small and thin and edges features on the image.
Sorry, it's just that
Yes.
these two
Sure.
pictures to be very much alike.
This one and this one.
Yeah, I don't know if it's because of the projector or
No,
but even on screen. But
No, here, I think I can tell the difference. So that one is more, more
There's
fine.
more resolution.
Yes.
Sure.
There's more resolution. So since here I filtered
This is more
large.
great.
yeah, but because then I was wondering, say, if you cannot trace the difference, this is the principle of compression for facts that you kind of eliminate features that the eye wouldn't see anyway, and you get a smaller size because you don't need that much space for you.
So I can say that I have actually a course on image processing techniques.
Yes,
There is a lot of some of more advanced techniques. Actually, do something like this: you take the image, you compute the inverse transform like this UV plane, and then you work on that space. And of course, you can do similar techniques on the direct image, something which is equivalent via the Fourier transform, but the most advanced techniques are precisely on the UV plane.
Yeah,
And
so
there are some fantastic things that you can do. Something that looks almost like magic.
yes.
Is this what the JPEG does? What, right? The JPEG file? I don't know if it's this exact principle. I'm just talking about image processing.
Yes, and in general, this has a lot of application not only to black hole physics, but also to medicine. Like you want to, you take a picture of an arm and you just see the veins. And well, this is a thin feature on the image. So you filter like small baselines and only allow large baselines to see like only this thin feature on the image. Here I'm going to apply to black hole image, and the thick structure is going to be the emission of the accretion disk, and the thin structure is going to be the photon ring, which is related to circular photon orbits. Okay, so I'm a little bit late on time. Just a disclaimer. Actual real life interferometers, they do not work as optical telescopes with a double slit on the top. They are actually more complicated. They are like we have here one dish, one radio telescope, the other radio telescope, separated by distance b. So this one collects the electric field of the source. This one also collects the electric field of the source. There is a tiny difference between them. Then you send this signal to what they call voltage multiplier, which is essentially to compute the degree of coherence. The electric field of the one times the electric field of the other. And then you have some correlator here, and this produces the visibility. But from the technical point of view, I don't know to tell you what are the technical difficulties. But
my understanding is that, for example, the signal from the left one, the leftmost telescope can actually be delayed, well, artificially before it's correlated, in order to kind of control this kind of observation. And at least that's the impression I have. Did you do something about this? Because you have these fixed telescopes, but you want to probe different directions on the sky. So how do you actually do that?
They are fixed, but actually the Earth is
that's two different things.
Yeah, but that changes already.
That's true. But even with the rotation of the Earth, there would be some directions in the sky that you would not be able to probe just with this alone. Right? You want to point out some specific direction?
Actually, maybe.
Yes, my point is just that actually.
Okay, that's true. That's good. So,
well, I am not sure if I am confusing two things because I am also not expert in this process, but I have heard from the people that does it. So indeed, actually, the main difference between this type of interference and the one that you do in optical telescope is that in this case you don't interfere things in real time, let's say. But what you do is that you record everything in a hard drive with an atomic clock. So you record the electric fields, and then these recorded electric fields are sent to a supercomputer that is the correlator, or well, not a supercomputer, but a cluster. And indeed, so as Pedro says, there is some. So you try different
delays
different delays
between the electric field of one and the other.
Right. So in this one delay, the series a bit, but this is to find where to get the fringes, because each of the telescopes so have their own atomic clock, but you have to be sure that they are perfectly synchronized. So this step of delaying the time is to find the fringes, and if you have more telescopes, then this is when the operation becomes very complicated.
Yes, but I confess that in this part, I don't know how it's done, but actually I think I answered it.
So like quite some years ago now, but I visited the radio telescope in Marseille, in France. And so they have a big one, but they also have small ones that do interferometry, and at the time, I don't know if they still use that, but they explained that, they had like the wires that go from the telescopes to the processing center were kind of matching the distance. So like say you have a one that is very close and one that is very far, they would have additional wire between the very close one and the center, so that the distance of wire would be the same as the one from the far one, to try to have this same kind of delays and compensating things. I don't know if it's still how they do it.
How about for the locally there? How about for the
Yeah.
Okay, so I will try to close it very fast. So now coming to application to black hole physics. What we can observe with that. So let's use again this result, which was derived with some very basic assumptions. And then we know that THT observes on 1 millimeter wavelength. And the separation between the telescopes is around 10 to the 7, which is the diameter of the Earth. The order of magnitude of the diameter of the Earth. So this condition here gives us an angular resolution in the sky, which is 20 times 10 to the minus 6 arcs of second. So extremely small angular resolution. And this is just to they comment that on the first letter of the 2019 results, and there is a limited diffraction of 285 milliarc seconds, which is essentially 10 to the minus 6. And can we observe a black hole with that? Well, depends on the black hole, because it depends on the size of the black hole, which is a scale with its mass, and depends also on the distance that we are from that black hole. So what will tell us if we can image a black hole with that is this factor here, g times the mass of the black hole divided by the distance to the black hole divided by c squared. Well, it happens that M87 is exactly on that window, on this window here that we can observe. So this scale here, theta 0, is around 50 milliarc seconds, and based on this very basic formula, we could infer that we can observe M87 if we know the distance and the mass of this black hole. And also the same holds for Sagittarius A.
But actually, you should put a factor there, right? Because
Yes.
is the factor of the
Yes, so if we put
but that's a factor of 3, which might be relevant here.
Yes, it's a factor of 10, I think. Yes, because if
So a 5.2 actually, it's current of 7.
Yes. Yes, for sure. Yes, this is like gives for mass and distance to M87. This gives like 3 milliarc seconds, and then we multiply by some factor, which then you arrive at this.
And in fact, if you put that, you get something very close to the value of EHT.
The value of EHT.
It's within error-bars.
Okay, so just to close, with this baseline here on the order of 10 to the 7, we can observe scales of this magnitude here. So around some dozens of milliarc seconds, which is essentially the scale of the emission of the disk. But and that's what we did, right? We see here that's what EHT did, and that's why we see here the emission from the disk. which is on this scale. But the theoretical prediction for the image of a black hole predicts other features than the direct emission of the disk. For instance, these features here that we see on the image, this image was obtained by ray tracing techniques, so it's a perfect idealized setup. The image that we would obtain if we had perfect resolution, like very far away telescopes. And this, for a Schwarzschild black hole, this is, if this direct emission, so the light that comes from the disk and reaches the telescopes, it's around 10 to the minus 6 arcseconds. This photon ring, which arises from the closed photon orbit, so it's a probe of the space-time geometry, of the curvature of space-time. It has a length of around 0.5 10 to the minus 6 arcs of second, milli arcs of second.
But that probe of the space-time geometry, but also a probe of the light source.
It also depends on the light source.
Because
Yes.
if it was an all-around scan, you wouldn't see that light source.
Yes, yes, it has a correlation.
So it's not really a probe just of the space-time geometry.
Yes, and this is the so-called n equals to 1 photon ring, and as you increase the number of photon rings, you have something that depends more on the geometry of the space-time rather than on the astrophysics of the disk, because it approaches the light rings, which is, I mean, a concept that you know well here. And just as a remark, the scale, so this angular size of the photon ring is much smaller than the angular resolution that we have, that EHT has right now with Earth-sized telescopes. So that's why we can see the emission of this, but we cannot see yet the photon ring. So what would be the distance between telescopes necessary to observe this at least this first photon ring? Well, using again this very simple formula, we can see that this is the distance between the telescope must be 10 to the 8 meters, which is larger than the diameter of the Earth. So it's not possible to see these features here in the image with Earth-based telescopes, because we need more even larger baselines the ones that we have nowadays. So to see thin structures on the image, we need large baselines. And to see this very thin structure here on the image, it would require a space-based interferometer. And well, this opens the part that we like. This opens possibility to investigate photon rings of some objects that beyond the Kerr hypothesis, because this is predicted for Schwarzschild, but it's not Kerr. But I mean, if you add the rotation, we would have something similar. But this is on the umbrella of the Kerr hypothesis. And if we we do not detect these photon rings, but if you want to investigate what should be the photon ring of a non-Kerr black hole, for instance, the photon ring of a hairy black hole, which has this very strange shadow, which is related to the photon ring. Then we have to apply this theory. We have to use the Bansitat-Zerling theory to see theoretically what we should expect at very large baselines larger than the ones that we have nowadays. For instance, we can also investigate, we can use this theory to investigate the interferometric signatures of compact objects without light rings, because in this case we do not have thin features on the image. So what should be very large interferometric results. And I mean, they are planning to, just to conclude, they are planning to build, there are some projects like BHEX that is planning to launch moon-based, space-based interferometers that in principle would be able to resolve to see these photon rings which are connected to the geometry of the space-time.
Sorry, you say moon-based?
I mean, space-based. Space-based, yes. So it should be on like 2 telescopes on orbit.
Okay.
Not the moon, no. Well, I think this is there is a nice theory to play with this type of theory, like the visibility amplitude, which is actually what the Event Horizon Telescope measures, and what you should expect that for the visibility amplitude, the interferometric patterns, if we have not a curved black hole but something else. And well, I think I that's a little bit of the time, but I'm sorry. Thank you.
So yeah, it's also because we had questions during the talk, but it was very interesting. So maybe we have the chance for 1 or 2 quick questions, but Haroldo is also here for a few days. So, is there any quick question? Yes.
If there is no more pressing question, I was wondering whether this kind of thin red lines.
Well, perhaps Pedro can explain better than me, but this is called cuspy shadows. So these are this is the shadow of a very hairy black hole, where the edge of the shadow has like this cuspies here, and this is a very non-curved signature of a black hole.
So that kind of filament is something that should be bright in an image.
If you put some accretion disk around here, this is going to left a trace, because I think that light rays that passes here is unstable photon orbit, right?
Sorry, I was.
Actually, it's asking what is this pink braces here on the.
So it would be a shadow edge, except that it's not doesn't respond to the threshold of light rays following the black hole. But would normally be part of the shadow. So it's kind of a continuation of the previous edge, if you see.
But is something that should show in an image bright or dark? Or?
So this has, it's unclear what it would happen with the realistic emission. So it's just on the shadow side.
I see.
So what happens is that, well, when you have the shadow edge, you have kind of a limit orbit that defines the threshold of light rays falling into or not into the black hole. In this particular case, you have 2 different sets that are kind of competing with each other, one which is more kind of inwards than the other. And at some point, there's kind of a transition of one orbit, class of orbits that determines the edge of the shadow, goes from one class to the other. And that creates this kind of, discontinuity in the derivative on the shadow edge. And this kind of pink thing is kind of the continuation of the previous one.
But for impact parameters close to these ones here, like it's an unstable orbit, it approaches an unstable orbit.
It's always unstable.
So maybe it's just a guess, I'm not sure, but maybe since it's an unstable orbit, as light gets closer and closer to this value of impact parameter, it tends to complete more and more turns around the black hole. And if you put an accretion disk, so each time that it turns around the black hole, it would capture more and more brightness. So, I mean, maybe.
But it would be actually something interesting to see with a realistic accretion disk, because in this case, it's not just a simple, probably, you wouldn't see just a simple photon, I guess. You see more complicated structure, precisely because of this transition. How it would be impacted by for me, it's not unclear. This would be future work.
Right. Sounds interesting.
Okay. So then maybe we can stop here. Let's thank Haroldo again.